Okay, so in the past we used graphical means in order to add vectors together. And the way we'll be doing it moving forward is actually using what we call Cartesian vectors. Cartesian vectors are basically breaking the vector up into x and y directions. Remember, we resolved into just general vectors or general directions last time. Now we're going to break into an x and a y direction. So we have an x direction like so in the horizontal and a y in the vertical, and they're 90 degrees apart, which makes our math much easier using trigonometry, which is the study of right triangles, which is essentially what we have here. Okay. Now, in breaking those up, we need to define what we call a unit vector. And a unit vector is basically this I vector and j vector, which is a vector that has a magnitude of 1, okay, in a specific direction. Okay, so this unit vector basically designates the directions of the x and y axis. So if I multiply any scalar times the I vector, I'm saying that that scalar, that magnitude is in the x direction. If I multiply it times the j vector, I'm saying it's times in the y direction. And because the magnitude is 1, I'm not changing the value of the magnitude. Okay, I'm just giving it a direction. So we could write a force vector like I have here as the force in the x direction times the I unit vector plus the force in the y direction times the j unit vector. So again, I have this magnitude fx in the I direction and this magnitude in the y direction, and I multiply that times the j vector. So this is how I would represent a vector in Cartesian form, using the x component times I plus the y component times j. Now, oftentimes we're given this force vector and I want to resolve it into the x and y directions. I essentially want to find the x component and the y component. Now, what I have here is a right triangle, right? Because x and y are perpendicular, we can use trigonometry to figure this out. Okay, so if I'm trying to find the x component, right, that's adjacent to this angle theta that I have here. Okay, so hopefully you remember from trigonometry that the cosine of an angle is the adjacent side of the triangle over the hypotenuse. So the cosine of theta here is f sub x divided by the magnitude of f. Okay, same thing for the y component. Okay, remember this magnitude and this magnitude are identical. So the sign is the opposite over the hypotenuse. So I have fy over here divided by the magnitude of f. Okay, now through algebraic manipulation, I can actually figure out that the x component is simply the magnitude of f times the cosine of theta, and the y component is the magnitude of f times the sine of theta. And we will do this hundreds of times during the class. So you're really going to want to figure out how to do that, and we'll do it in class and figure it out from there. But that's how we represent a vector in Cartesian form. We break it into x and y components, or horizontal and vertical components, using I and j vectors and using trigonometry. Now, once we do that, we can talk about vector addition. And really, this kind of picture I have up here is why we would do it this way, because we can easily add 3 or more vectors together using Cartesian vectors. Using the graphical approach, I can really only do 2 vectors at a time, and this way it works much more efficiently when I have several vectors. Okay, so the first step is to break each of these vectors, f1, f2, and f3, into its Cartesian form, form. Basically, find the x and y component of 1, the x and y component of 2, and the x and y component of 3, recognizing that, for example, f2x here has a negative sign because it's acting to the left in the negative x direction. Positive x is to the right, positive y is up. Likewise, my f3y is negative because it's acting down, positive y is up. This component is acting down, so I have this negative sign here. So the first step in adding forces is to break them up into their x and y components. Okay, and we do that just like we did on the previous slide using trigonometry. Once I do that, I simply add up each component. So I take my x components, my f1, my f2, and my f3, add them up, and my fy, f1y, f2y, and f3y, add those up. Okay, and so I take this one, I subtract off this one, and then add f3x. Likewise, f1y plus f2y minus f3y. And what I wind up with is the resultant force in the x direction and the resultant force in the y direction, given like this. And I can write that vector like this, where I have the resultant force equal to the x component that I summed up times I plus the y component that I summed up here times j. Now, if I wanted to find the magnitude of, say, this resultant vector, or really any vector, I can just take and use Pythagorean theorem, knowing that this side plus this side equals the hypotenuse squared, right? This side squared plus this side squared equals the hypotenuse squared. So I take the square root of that, and I can get the magnitude, basically the length of this vector. If I want to find that angle, I simply use an inverse tangent, right? Here's my y component, here's my x component. Divide those, take an inverse tangent. So that's how we're going to add vectors moving forward, right? Break each force up into x and y components, sum up your x's, sum up your y's, and solve for your resultant force, finding a magnitude and angle if that's necessary. Okay, here's a problem applying what we've learned about adding coplanar forces in using Cartesian coordinates. Okay, so I've got two forces here, FA and FB, and I want to find the resultant of those two added together. Okay, so FA is 700, angle of 30, FB is 600 with an angle of 20. So what we're going to start with is summing up in the x direction. Okay, so in the x direction, I have FA here. The x direction, if I think about it, the triangle going right along here, okay? The x, the horizontal component, is opposite of the 30, so I'm going to use sine 30. So it'll be 700 sine 30, and that's positive because it's going to the right, okay, where x is positive. FB is going to the left, so it gets a negative sign, okay? And the horizontal is actually adjacent to this angle theta, okay? So I'm going to use cosine for the horizontal component in the x direction. So that'll be 600 cosine 20. Okay? Plugging that into your calculator, adding it up, I get negative 213.8. So that's acting to the left at about 214 newtons. In the y direction, okay, this time on FA, the vertical, which is the y direction, is adjacent to the 30. So I'm going to use cosine for the adjacent to 30, so it'll be 700 cosine 30. Let's put it right here. For FB, the vertical on the triangle is over here, okay, which is opposite, so I'm going to use sine, so that'll be 600 sine of 20 degrees. Adding those two up, okay, I get 811 newtons moving upward. So what that looks like on a graph is right here. So I have 811 straight up and 214 to the left in the negative x direction. So my resultant force is the combination of those two vectors in the x and y direction. Okay? So it looks like this. Okay. It's asking for the magnitude and the orientation, so I need to know the length of this and that angle theta that we have defined there. Okay? So to find the length of that vector, I just use Pythagorean theorem, which is the square root of the sum of the squares. So square root of 214 squared plus 811 squared equals that. And again, the negative gets dropped because I'm squaring it anyway. A negative times a negative gives me a positive. So I just use the magnitudes. I just drop my negative here. So that's where that comes from. And I get a magnitude. The length of this side then is 839. This angle is going to be the inverse tangent of x over y. So that 213 over 811. Okay, and again, I have the angle defined from the vertical. It would be different if it was defined from the horizontal, but this is the angle that we're looking for here. So from the vertical, okay, it is the inverse tangent of opposite over adjacent. So 214 over 811 giving 14.8 degrees. In this problem, we want to find F1, one of the forces, knowing the fact that I have a resultant force that equals 600 newtons along this U-axis. So I'm giving F2 and F3 and the resultant force, and I want to find F1. Okay, so the first step that we need to do is we need to write each force in Cartesian form. That is, find the x and y components of each of the forces, each of the three forces as well as the resultant force. So my unknown force is actually F1, okay, and it's at an angle of phi from the x-axis. So I have F1 cosine since it's adjacent to the x-axis, and F1 sine in the y-axis since it's opposite of that phi. Okay, so F2 is the 650 in the x direction, and it's going to be 3/5 because 3 is on the horizontal, 5 is along the hypotenuse, so it'll be 3/5 in the x direction, and that's heading in the negative x direction. Okay, so 3/5 times 650 is 390. The vertical is 4 over the hypotenuse, so 4/5 times 650 is 520, and that's in the positive y direction. Moving on to F3, that's the 500 newtons. That's going to be sine and cosine of 45. Now, of course, 45, sine and cosine of 45 are equal, so it's just 500 cosine 45, 500 cosine, or sine. It would be the same thing. And that would be in the positive x direction and the negative y direction. My resultant force is going to be, again, 600, given here in the problem statement, along the u-axis, which is 45 degrees above the x-axis. So that's also going to be sine and cosine of 45 in the x and in the y direction. So I have the magnitude or the component of each of the forces in both the x and y directions. My unknown here is actually one of the forces I'm adding together. I know the resultant in this. So now when I add up the x components and add up the y components, I'm solving for something other than the resultant. So in the x direction, my resultant in the x direction is 424.6, and that's going to be equal to F1 plus F2 plus F3 in the x direction. So that'll be F1 cosine of phi minus 390, again because F2 is going to the left in the negative x direction, plus 353.4, which is the x component of this 500 Newton force. Okay, so solving that for F1 cosine phi, I get 460.7. So again, I'm solving for something other than resultant. Add up each of the components and set them equal to the resultant in this case. I do the same thing in the y direction, where I'm going to have my resultant in the y direction is 424.26, again because I'm at a 45-degree angle. It's the same. Okay, then I'm going to have F1 sine of phi plus 520, which is the y component acting upward for F2, minus 353.53, and that's because this 500 Newton force is acting downward in the y direction at an angle of 45 degrees. So that's my other equation. Solving that for F1 sine phi, get equal to 257.18. Now I have two equations and two unknowns, right? I don't know F1 or phi, and I have this equation as well as this equation. Now if you remember from trigonometry, I can simply divide these equations. Okay, sine divided by cosine gives me tangent of my angle phi, which is going to equal 257 over 460.7. Okay, doing an inverse tangent function on that, I can figure out that my angle phi is 29.2 degrees. Plugging 29.2 degrees in either one of these equations, I can solve for F1 and find that it's 528 newtons. So again, with these Cartesian problems, you write each force in both the x and the y directions, sum up the forces you're adding together and set it equal to your resultant. You're not necessarily always finding the resultant. In this case, we had the resultant. So you're solving for a different force than the resultant. That would be F1 here. So you add up each of those forces, set it equal to the resultant in both the x and the y direction. Two equations, two unknowns, and you can solve the problem.